So thank you all for coming to the annual Clay Lecture. The Clay Fellowship was established at the CFA by Landon and Lavinia Clay in 2000 and has become a premier fellowship since then. Landon passed away in 2017, and the leadership of the family finances has passed to one of his sons, Thomas. He lives in Boulder, Colorado, and sends his regrets he's not able to join us today. But I think there's a fairly significant chance that he'll actually watch this on the YouTube video. The Clay family was actually very invested in intellectual pursuits. They endowed the Clay Mathematics Institute, the Clay Millennium Math Prizes, and they endowed our participation in the twin Magellan telescopes in Chile. One of the telescopes is the Magellan Clay Telescope, and it's one of our more successful investments. There have been 23 Clay Fellows altogether, including the Clay Fellows who are here with us today. I'd just like to draw attention that Vicky Caligera, the first of the Clay Fellows, was elected to the National Academy a little over a year ago and had her first NAS meeting last month. But we have alumni of this program at Toronto, here at the CFA, Warren Brown was a Clay Fellow, at MIT, at Berkeley, and at Leiden, and soon Caltech with our current speaker. So Vikram was almost born in Australia. He got there at a very young age. But he was educated fully in Australia, did his undergraduate education at ANU, and spent a year in Berkeley, and then returned to Australia to complete his PhD at the University of Melbourne in 2014. His doctoral work was on radio pulsar observations to search for gravitational waves from binary supermassive black holes, and that thesis was awarded 2 prizes, the Charlene Heisler Prize of the Astronomical Society of Australia and the Stefano Braccini Prize of the Gravitational Wave International Committee. He then took up a Millikan Fellowship at Caltech, where, among others, he worked with Greg Hallinan. And he came a year ago as a Clay Fellow, but that's probably all he's going to spend with us, because he's going to take up a junior faculty position at Caltech over the summer. So with that, I'll give the floor to Vikram.
Awesome. Thanks, Charles. And yeah, it's been really great to be here over the last year, and I hope to tell you a little bit about some work that I've been doing over the last, I guess, few years, but somehow there seems to have been a flurry of work in this last year in particular. And so the story that I'd like to tell you starts pretty much here. This is the Parkes radio telescope in Australia. It's very pretty and quite large. It's a 64-meter diameter dish, and you actually observe sitting in one of those rooms down there, which is kind of scary when there's a lot of wind buffeting the thing around. And so in 2013, as a grad student, I was sort of getting a bit over simulating things, unfortunately, and with Ryan Shannon pictured up there, decided we actually noticed something strange, that something like 20% or so of the time allocated on the telescope was actually not being used for various reasons, for wind stows, perhaps maintenance as well. And so we thought, why don't we actually take up all this time? You know, it's there. In particular, we wanted to search for fast radio bursts, FRBs. These can happen almost anywhere in the sky, and so you can do it while the telescope is just pointing straight up. And so we proposed for 0 allocated time, gave our proposal a very corny name, and we ended up actually getting about 50 hours of allocated time to do tests. Now, we weren't quite sure what these tests were that we were given the time to do, but nonetheless, we drove down to Parkes. I think we were the last people to actually observe from the tower. After that, it became remote. And so we drove down to Parkes and thought, okay, let's point at a nearby dwarf galaxy. This was very early in the days of FRBs, and no one really knew anything about their distance scale or where they could possibly come from. And so we thought, what if there's an extra source of dispersion that we don't know about? And sure, let's just point at a dwarf galaxy. Try it out. So after an hour of tests, About 20 minutes into our first observation, we saw our first fast radio burst. To put that in context, Parkes typically takes about 300 hours to find an FRB. So we were very excited, of course, right? This is probably 3 in the morning. We thought we'd seen things. And so we spent the next few nights, actually, we got an amateur astronomer to point the little 12-inch telescope at the same location, and we pointed Parkes at the same location. And, we kept going on and on and on. And then, because this was also the first one that people saw sort of in real time, like when the burst went off, we could do various kinds of follow-up. We went to the Australia Telescope Compact Array, imaged the field over the next couple of months, and even more amazingly saw a flaring source. Now, we were super excited. We've got a coincident, potentially afterglow. What's going on? We've got some Gemini time, got an image, found a little sort of almost blended point source with another slightly brighter source. Everything looked very exciting until, we pointed at the same field for another 300 hours at Parkes and saw nothing. And 2, this thing is most likely an AGN from its spectrum, and it turns out that, surprise, surprise, flat spectrum AGN do occasionally flare. Anyways, so nonetheless, that sort of got me all excited about the field, which is why I'm here today, I suppose. And so, what are fast radio bursts? What we do to search for these things is we take radio spectra very, very fast, in this case with 64 microsecond time resolution. And then we play it forward, and if we're lucky, we see a fast radio burst. Playing this a bit more slowly, what you actually can see is that the burst arrives sooner at higher frequencies and has this quadratic delay going down to lower and lower frequencies. The delay is because of dispersion in sort of plasma between us and the source. And the single most important thing about FRBs that you need to remember is that they're dispersion measures which quantify the amount of delay in units of the intervening plasma column. Their dispersion measures are more than what are expected from the Milky Way. That's the single biggest reason why we think these things are extragalactic. And to put some numbers to this sort of thing, for a typical extragalactic dispersion measure of about 300 parsecs per centimeter cubed, and if you just assume that the DM comes almost entirely from a constant density IGN, you end up with a distance scale of about a gigaparsec. These are sort of the numbers to keep in mind here. And so we currently have about 70 fast radio bursts in hand, with hopefully many more to come in the coming year. Initially, they were discovered in sort of reprocessing of archival data from Parkes. You can see here that some of these are found towards the small and large Magellanic Clouds. That was intentional because Parkes was searching for pulsars in those locations. Once they were discovered, some around 2007 or so, people started to initiate more and more surveys, now targeted at fast radio bursts. So yeah, this is roughly when they were discovered, and very soon you will see more fast radio bursts appear here. And what I want you to look out for, especially as we get to the end of this movie, is the sheer sort of almost exponential increase in the detection rate. So now we've sort of got one more down there, a few more appeared here. You can see this, they're appearing at sort of high galactic latitudes. That one is from the Green Bank telescope, the first one seen at another telescope. And there's Arecibo. It found one in the plane, surprisingly enough. We'll come back to that one later. Parkes now finds a few in the northern galactic sky. And then, very soon, things start to get a bit wild. You'll see in a minute, the refurbished Molonglo telescope Utmost starts to see a few over here. And then the Australian SKA Pathfinder, ASCAP, sort of takes over the field. You've got all these grey points. They did a survey at a lat of -50. This clustering is not real. And yeah, there's CHIME. You might have noticed the the sheer sort of speed which CHIME discovers things, and we look forward to many more discoveries in the coming years. And so this is kind of the sample that we have in hand at the moment. this is probably the last time I'll be able to give a talk like this, where I can actually focus on a few individual bursts. Because as you can see, the detection rate is exploding, and soon we're going to very much be in sort of two regimes. One regime being the regime where we have thousands of fast radio bursts. This is not an exaggeration. And two, the regime where we will actually be able to say things jointly about fast radio burst properties and their host galaxies. We can't do either of those yet, and so what I'd like to do is take you sort of through a retrospective view of the field. In the hope that I think by looking backwards we can try and better interpret the amazing results that are to come over the coming months and years. And so this is what we've got. We've got something like 10 to the 3 over the entire sky every day. They're bright. All are over a Jansky in their peak flux. Some go up to kilojansky. They're really bright. And of course, their dispersions are larger than expected from the Milky Way. Other reasons why we think they're extragalactic is that we observe both Faraday rotation and signatures of multipath propagation that are also much more than expected from the Milky Way. Where they originate is a very important question that I might say a few words about in this talk. And so we think these things really are at distances over a gigaparsec or so. This is not like the case of LIGO, where we're talking about a few tens of megaparsec distances in some cases. These things are really far away, or so we think. That implies an energy scale in excess of 10 to the 42 ergs per second. These are luminous. Some of them are as luminous as the most luminous quasars when they're on for about a millisecond, which is not very long. All the fast radio bursts that I showed you in the previous slide were discovered with single dish telescopes. And so we don't really know what their host galaxies are. And so all we really have about all those fast radio bursts, at least when we discovered them, is just this roughly millisecond duration event once you take out the dispersion. And that's it. That's all we've got. And that's what I'm going to base a lot of this talk on.
What sort of angular resolution accuracy?
So when we discover them, it's typically a few arc minutes. But then one has been localized because it repeats, and so you could point an interferometer at it. And so to put some more numbers to the distance scale, what I'm showing here is a histogram of dispersion measures, extragalactic dispersion measures, which, remember, quantify the column density of plasma. And I'm showing them for 3 different telescopes. One, I don't want you to read anything into the top histogram. It means almost nothing because I've not corrected for any sort of per telescope systematic effects. But I do want you to take a little look at the differences between the blue, green, and orange histograms, which come from CHIME, ASCAP, and Parkes, respectively. In particular, it does appear from this that, small number statistics aside, Parkes does typically see slightly higher dispersion measure FRBs than at least ASCAP. That, it turns out, is something that's almost real because the ones that are at higher dispersion measures also seem to be slightly fainter. That's nice, right? It means that things that are closer, if we take the dispersion measure to mean to sort of be a proxy for distance, it means that things that are closer are somewhat brighter. That's good. We've got an evolving population. And you can see this here where I plot fluence versus dispersion measure. And these points up there are from ASCAP, and these points down here are from Parkes. The ones in the middle are from Molonglo, and this is a spread of events from the first repeating FRB, one of 2 published events that repeats. The others have not yet been observed to repeat. And so this suggests that we really do have an evolving population, which in turn suggests that we're seeing things at moderately large, almost cosmological distances. Another bit of information on sort of going into that is that, like I said, the first localized FRB actually has a host galaxy at a distance somewhat consistent with its extragalactic dispersion measure. It's at a gigaparsec. It's kind of nice. And I'll say much more about this a little later, but I'll also mention that those FRBs which have sort of a few arc-minute localizations, so not several tens of arc-minutes, but just a few, like this one over here, don't sort of have an egregiously large nearby galaxy within the localization regions. And so that does suggest a fairly large distance scale for the majority of the population. So once we know that, we'd like to know something about the rate and the source counts. And so this is probably something that has been among the most controversial issues in the field. How often do they actually occur, and how many are there at different brightnesses? And so people typically quantify the latter with a power law index. We say that the number at different brightnesses scales as a power law function of brightness. And the power law index, some people claim it is up to 3.9. Others, I was very much second author on this paper, claim it's as low as 0.6. This is a very large spread in source counts. But there are many reasons why you should not look too closely at that. And I think it's summarized in this plot by myself and Avi, which we published this year, where you can sort of see various curves which show sort of semi-realistic source count. So this is again plotting the number of events above a given fluence as a function of fluence. For a uniform population in Euclidean space, if you just got, imagine standard candles, for example, very nearby to the Earth, you would expect this to scale as fluence to the -3/2, like these power law dashed lines there. However, when you account for the possibilities of having sort of non-power law intrinsic spectra, then you have to account for a K correction, or even consider different types of spectra, and also potentially the effects of broadening due to multipath propagation through inhomogeneous plasma, you can end up with a whole family of curves. And the problem of comparing different telescopes to each other is that one telescope might be sensitive and so observing up here, other telescopes might be much less sensitive and so observing down here, and you'd see vastly different power law indices. And that is actually probably what explains the big scatter in the previous plot. It's kind of nice, but there's still a long way to go. What I would like you to look at, though, is this plot here, which shows what I think are the most robust constraints on the volumetric rate of FRBs. And so what I'm plotting is the 90% confidence lower limit on the volumetric rate as a function of the amount of dispersion measure I ascribe to the host galaxy. And so, for example, if the source were to sit in something like a moderately sized early type or a dwarf galaxy, people suggest sort of fiducial dispersion measures around here, 23 parsec per centimeter cubed. For a face-on late type galaxy, of course face-on being the least likely orientation, you end up with something like 35. This is the median over a large number of sight lines. And so what you can see here is that the lower limit on the rate, this is based on the recent CHIME publications, the lower limit of the rate, especially if you sort of take a moderately realistic host DM, ends up being comparable to the core collapse supernova rate. Now, FRBs are millisecond duration things, which look a lot like what you might expect, like an extreme version of, for example, pulsar emission. But whatever it is, whatever your favorite model for what FRBs are, it's kind of difficult to make a rare, strange product of stellar evolution faster than the core collapse supernova rate. And so I think that this really does suggest that if we believe that FRBs are the product, originate from the products of stellar evolution, then it's likely that the sources emit multiple bursts over their lifetimes. And I'll come back to this theme a little later as well. And so what are FRBs, right? We don't know yet, leaving that aside. But I'm not going to, and neither am I going to lay claim to one particular model, although it depends on how loose you want, how tightly you hold me to what I say. An FRB theory has to explain three things, in my opinion. One being the sheer energy release. And so FRBs, like I said, have luminosities of something in excess of 10 to the 42 ergs per second. Their isotropic-equivalent energy releases actually range from 10 to the 38 and 10 to the 43 ergs, depending on given the range of the population. Then, if you assume that the emission region has to be smaller than the light travel time sort of across the source, then the millisecond timescale implies a very small source. And then you can do things like estimate, for example, the energy density and the equivalent magnetic field, energy density, and basically what you end up with is a neutron star. There's no there's no two ways of saying that. The second thing you've got to explain is, of course, the escape of the radiation from the progenitor environment. You can't just emit the thing, it's got to get out. And it's particularly hard for radiation to escape when it is at very, very high brightness temperatures, like FRBs. We're talking a few times, 10 to the 35 plus Kelvin in equivalent. And so, especially if one were to invoke a very exotic source that were very young, it's important to consider how you're going to get the radiation out without it being absorbed. Then the third thing that I think that any theory has to explain is, of course, the high volumetric rate, which I would say is larger than the birth rate of candidate progenitors. And so you can't really, in my opinion, you can't make these things just once. You've got to make many, at least a few, if not many, per source. And so, theories and FRBs. There are many, many, many extant theories of what FRBs are. What I'm plotting here is the number of FRBs with time in blue, and the date at which the first paper on each individual theory was published. And so you can see structure here. This is not just an idle exercise, although there's a little bit of that. So you see, first of all, that after the first burst, the Lorimer burst was published. There were of course a few theories. There was then a sample of FRBs published by Thornton et al. In 2013, at which stage there were actually more FRBs than theories. It's amazing. And then theorists, of course, got their act together and started to go forth. And if I were to put a few more events here, you can see a few actual trends. I'll highlight in particular the discovery of the first repeating FRB seemed to lead to a slight uptick in the number of theories, and then its localization and then host galaxy properties led to another uptick. But we are now, and I can't emphasize enough, we are now squarely in the regime of many more FRBs than theories. This is actually, there are 13 FRBs missing from this plot from Chime recently. We definitely have more FRBs than theories now. We're not quite the regime anymore. But I must say that it was quite fun to work sort of at this time when you really could say whatever you liked, and you weren't obviously wrong anyway. But one of the reasons for why there are so many theories is that we don't really know what an FRB is, even observationally. In that we don't really know the limits of the observed properties of FRBs. I've said that they have millisecond durations, but how many are there at 50 millisecond durations? We just don't know because we're not very sensitive to 50 millisecond events. Are there FRBs with dispersion measures in excess of a few thousand parsecs per centimeter cubed? We don't know because, again, we're not very sensitive. Similarly, we're not really sensitive to FRBs that are very narrow on microsecond timescales. We just don't know what the range of the FRB population is. And certainly some of these trends, especially the one between dispersion measure and fluence, may suggest that we're only beginning to scratch the surface of the FRB population. And one way of illustrating this is to consider a few cases. The first is the one and only FRB from the Green Bank Telescope, published by Masui et al. Now this one is a very nicely behaved FRB. It has a very nicely shaped pulse. It has, when you fit the structure, you end up fitting it with a sort of normal pulse convolved with a one-sided exponential. There's a slight exponential decay to the pulse. This turns out to actually be frequency dependent, which is characteristic of multipath propagation, which is nice. So this thing is propagating through an inhomogeneous medium. And so it's also polarized and Faraday rotated. The rotation measure is reasonably high. It's sort of not crazy, but not it's very nice. It's like it came from sort of a star forming region, for example. Another one turned out to showed us that FRBs can be quite bright. This one has structure in its spectrum that's in this case saturated at a kilojansky in this plot. Its spectrum shows these very nice striations, which we interpret as scintillation, which is due to now whatever process created this delay in the pulse occurring on microsecond timescales, where you get constructive and destructive interference of the delayed rays. That causes this pattern. It, however, has no detectable extragalactic Faraday rotation, suggesting quite a clean sightline through which we're viewing this. Third, though, is the repeating FRB, the original repeating FRB, where, well, one, it repeats. That's an obvious difference. Besides that, it's not scattered at all. There's no detectable extragalactic scattering. However, its Faraday rotation measure is something like 1.4 times 10 to the 5 radians per meter squared. You know, several orders of magnitude in excess of this one, and of course this one as well. You can see here the modulation of Stokes Q and U with frequency over a fairly large band. It's a really beautiful detection. This is actually of just one pulse. It's kind of an amazing detection. And so we have this massive diversity of properties that theories have tried to explain, which has been a very difficult task. So what I'd like to do is focus in particular on the repeater, because it's the one for which we have by far the most information to try and get at what's going on. I do think that although it repeats, although it's different from the others in many ways, it may well be a sort of a Rosetta Stone of FRBs in the way of trying to actually get at what makes these things. And so one of the reasons for that is the nature of its host galaxy, pictured here in the Hubble image. You can see this sort of weird sort of cometry-shaped galaxy. It's only a few times 10 to the 7 solar masses, which of course means it was quite a heroic effort to study this thing at a gigaparsec distance. That little white cross indicates the location of the FRB, but it also indicates the location of a persistent radio source there as well. And it turns out that this red circled region seen here in the schematic diagram is also a very bright star-forming region, forming stars at about a solar mass per year. It's basically a starburst dwarf galaxy. But that's not all. This FRV is really weird. So if you look at some of the pulses from this thing, it's now seen in frequency versus time, and we've actually removed the dispersion here, but selecting for the maximum amount of structure in the pulse profile, not the maximum signal to noise. It turns out that these pulses are incredibly structured and almost always have this, these sort of spots that trail down to lower frequencies with time. These are all de-dispersed the same dispersion measure, as is this one, which, as you can see, has a slightly different structure, which may indicate a slight change in the dispersion measure over a few years of this thing. That's one thing. The other thing is that its rotation measure over a fairly large timescale has almost monotonically decreased by quite a large amount. I mean, a few tens of percent here is how much it's decreased. And it sits right in the middle of this persistent radio source with which it's co-located to within about 40 parsec with VLBI resolution, which also happens to have a very weird spectrum on its own. This particular source is unresolved with VLBI, and it's a flat spectrum source at low frequencies with this tail off to higher frequencies. And so Brian Metzger and collaborators put together what they call a concordance model that looks something like this. I'm not going to explain what each layer in this onion is, but I'll highlight a few things. This particular model is able to explain the radio bursts. It's able to explain the rotation measure. It's also able to explain the decline of the rotation measure, and is able to explain the radio source itself and its spectrum. And you do this by having a central engine, which in this case is a magnetar, a very highly magnetized neutron star with something like a few tens of a millisecond of spin period. And it needs to constantly keep flaring over and over and over again. And as one flare runs into the ejector of a previous flare, that's when the claim is that the FRBs are generated. So I'm not going to say much more about this, except to say that I think this is a very promising model that can be tested in various ways, and it may give us some clues about what at least very young FRBs look like. And one test in particular that I'll highlight is that, and this will be of interest in particular to the EHT and SMA people in the room, is that one test that Harish Vedantha and I realized could be applied is Faraday conversion, which is a really nice effect where in the presence of mildly relativistic plasma, one can convert mildly relativistic plasma in a very strong magnetic field. You can convert linear polarization to circular polarization. You don't just convert between Q and U, you convert between QU and V as well. And so our prediction is that given this concordance model, circular polarization with fractions of certainly above 10% and up to almost unity should be detected in this FRB, if not at the frequencies where it's been observed previously, like a few gigahertz, certainly at gigahertz. And I think early signs seem to be promising that this is in fact the case. I think that's this is probably one of my favorite ways of actually getting at actually testing some of these very complicated but quite predictive FRB models. And so, moving on. So remember how I said that there is an amazing, incredible diversity of FRB properties. We have some that are viewed along amazingly complicated sightlines, like the repeater, and some that are viewed along amazingly simple sightlines, like some of the bright bursts that we've seen. And so there's quite a bit of hope in the community for using FRBs as probes of unseen matter in the universe. And I mean two types of matter in particular. One, I mean very hot, diffuse baryons at low redshifts, where halo virial temperatures approach 10 to the 7 Kelvin, and it becomes quite difficult to see the majority of baryons. Some people refer to this as various varieties of the missing baryon problem. And also matter that exists in very small scales. So in particular, I mean roughly parsec scale inhomogeneities in circumgalactic media of galaxies, as well as potentially primordial black hole models for dark matter. And I'll say a little bit about, in particular, the circumgalactic medium aspects of what FRBs can do. I also mentioned one thing, which is that, I'll highlight one thing, which is that, again, dispersion gives you the total column density of plasma. Observations of multipath propagation manifested as scattering or scintillation tell you about the small scale structure. And the Faraday rotation, of course, tells you about the magnetic fields. And so the circumgalactic medium of galaxies is, of course, amazingly complicated, and in particular, observations recently by the COS Halos team have revealed all sorts of amazing phenomena in the gas surrounding galaxies. But the key things I want you to remember are that galaxies are by no means all the baryons within halos. There is, of course, a lot of gas surrounding them. And there's several lines of evidence suggest that this gas exists in multiple phases, between 10 to the 4 up to 10 to the 7 Kelvin. And this gas is very hard to see, as shown in this simulation, where on the left, this is from the FIRE team, you see gas density, and on the right you see gas temperature. This expanding circle indicates the virial radius of this roughly Milky Way-sized halo. And we're now at just below redshift of 1 in the simulation. And what you can see here, and I'm just going to pause this, if I can. Nope, I can't. I'll play it again. What you can see happening is, well, a few things. One is that you have various complicated mechanisms at work here, but ultimately you end up with this fairly diffuse gas, with projected gas densities of well under 10 to the minus 3 grams per centimeter squared, at temperatures of something like 10 to the 6th Kelvin or above. This gas is very hard to see. For one, X-rays, of course, the emission measure is incredibly low, and so it's very hard to detect this gas close to the virial radius in emission and in absorption, as people do with distant quasars, especially with UV and X-ray spectroscopy. Again, 10 to the 6 Kelvin gas is very hard to see for various reasons. FRBs can detect this gas. How do we do it? The way we plan to do it is basically by trying to account for all the sources of dispersion along the lines of sight. I'll remind you that you might use FRBs, potentially have some sort of circumburst medium if they live in unusual environments. They might have, of course, they will have some host ISM. Then there is also the halo of the host galaxy. And then on the Milky Way side, there is a Milky Way halo and, of course, the Milky Way ISM as well. These can, in some cases, be very complicated things to model, but in other cases, they're thought to be quite straightforward things to model. But in general, when people do a synthesis of various FRB models as well as sightlines through host galaxies, we think that we can sort of get away with about 50 parsecs per centimeter cubed of uncertainty in the host properties and about 20 on the Milky Way side. And again, to remind you, FRBs at several gigaparsec can have DMs of about 1,000 units. And so we hope to model these ones out and then account for intervening galaxies in order to ask what baryon fraction is in the halos of intervening galaxies and what baryon fraction is outside the halos of intervening galaxies. And this is a fundamental question because we don't really know at low redshifts where the majority of cosmic baryons are located. Are they in the IgM filaments or are they locked within galaxy halos? This is an important question to try and answer. And it suggests that even a few tens of localized FRBs with reasonable follow-up observations. In particular, we think that out to a redshift of 1, we can account for more than 50% of the halo dispersion measure with just pan-stars observations. With just a few tens of FRBs, we think that we can do this. I'll emphasize that these are localized FRBs, not FRBs with current localizations, but arc-second localized FRBs. The next thing that we can do, and this is the second thing that I think is quite important for the CGN, is we can interpret the observations of scattering of FRBs. Now, scattering is an amazingly rich and complex set of phenomena observed in the Milky Way itself. However, in our case, we like to think of it in a fairly straightforward way. Imagine plane waves intersecting some sort of a screen of electron density fluctuations. The screen distorts the wavefronts, resulting in the bursts, in the most extreme cases, appearing to arrive from multiple directions with appropriate delays. The delays, for a reasonable distribution of density fluctuations, will end up causing any incoming pulse to be convolved with a one-sided exponential. And so that's how you get these sort of shapes that we observe in about a third of all FRBs. Now, we actually think that there's a relation between the timescale of these delays, the scattering timescale, and the dispersion measure. Well, maybe not a relation, but at least if you look at plots like this, and a similar plot was published by Chime recently, you find that FRBs at very high dispersion measures, up here, generally turn out to be scattered, whereas FRBs at lower dispersion measures, down here, generally do not have detectable scattering, even though we would be able to detect them in many cases. There is definitely a selection that prevents us from seeing things in this part of the plot, but not in this part of the plot. We're complete down here. And so there does seem to be an emerging relation between dispersion measure and scattering, which suggests that the medium that causes the dispersion also potentially causes the scattering. And that's exciting because in models for the multi-phase nature of the CGN, in particular published by McCourt et al. Last year, the idea is that the CGN cools from very hot 10 to the 6 and above Kelvin gas all the way down to 10 to the 4 Kelvin clouds on parsec scales. This is kind of amazing because how can we ever... It's amazing in many ways. One way is that I think one of the conclusions of the McCourt paper is that you could probably never test this prediction. How do we ever observe parsec scale structures in the CGN? So it turned out, though, that Harish Vedantam and Sterl Finney, as they published this year, found that this particular model, when you try and put it in some sort of a semi-analytic model, taking the properties of the CGN out to large redshifts, accounting for the radiation field, and so on. This particular model has very strong predictions for fast radio bursts. In particular, we think that robustly to, for example, the volume filling fraction of the clouds, you always end up with an increasing scattering timescale with redshift. That is, I mean, of course, the normalization of this depends quite sensitively on your model for the CGN, but you do generally predict higher amounts of scattering at larger redshifts, and detectable amounts. I mean, this here is a millisecond scale, and FRBs, of course, are millisecond duration bursts. I think that this is a very promising way to start to test some of these CGM models as well. And so just to summarize where we're at now, this is a really, really interesting time in the field. We think that FRBs, we're beginning to have some small insight into what FRBs actually are. We think that they are outbursts of compact objects, the most extreme kind of outbursts. We think that multiple bursts are generally emitted over the source lifetimes. And I would say that at least the modeling, the theoretical community, is being pushed towards extreme versions of neutron stars. I would also argue that we're only beginning to skim the surface of the total number of properties of FRBs. I certainly don't think that we've seen all the FRBs there are to see so far. And I'd also say that they are very promising probes of baryons at low redshifts, both the total contents and the smallest scale structures. And so what's next, right? Well, two things. Many, many, many FRBs, for one, and two, arc-second localized FRBs. I'll highlight again, this is a picture of the CHIME telescope in Canada, which was designed, of course, to do H1 intensity mapping, but various people, including Vicky Caspi, realized that one could use this as a very effective FRB search instrument because it's basically got the sensitivity of the Green Bank telescope, but the field of view of about 225 square degrees on the sky. It's an amazing instrument, and we look forward to many results from CHIME over the coming months and years. Second, I strongly believe this is the year when we will have the first handful of arc-second localized FRBs where you don't rely on repetition to localize them. Arc-second localization at the first instance of detection. And so why is the latter important? Well, there are two questions that we're most interested in the field. One, of course, is what are FRBs? And two is how can we interpret their propagation signatures to get at the intervening material? Well, localization gives you a lot. For one, you get the host galaxies, which give you a redshift. You also have the host galaxies, which give you the properties of the host galaxies. The redshifts give you things like volumetric rates. These are really basic quantities. We're at the stage where we don't have a luminosity function. We know almost nothing about the properties of the host galaxies. And then, of course, in more subtle ways, we'd like to know something about the environments in which the bursts originate from, in multiple ways, one being the actual locations within the host galaxies, so that you can sort of start to make the same arguments that people did with GRBs in the past, and sort of the offset distributions from the host light. And of course, accurate localization does give you the opportunity to find faint multi-wavelength counterparts, which you cannot find with the very large localizations we've had so far. Of course, on the other side, localization is crucial. Without localization, you don't have host galaxies. Without that, you don't have redshifts, and without redshifts, you can't do almost any of the science with intervening matter. Localizations are key, which is why over the last few years, I've been, I guess, mainly involved in trying to build instruments to try and localize FRBs. We haven't localized any yet, I won't leave you in suspense, but I think we've got a very promising path ahead into the coming year or two. And so these instruments are based at the Owens Valley Radio Observatory in California. This is a picture of it down here. It's a very beautiful place. So this is a sort of a wide-angle view of the site on which there are actually many instruments. This, of course, is the home observatory of Karma, was shut down a few years ago. And in fact, you can see many of the Karma dishes sitting down there right now. But what's happening on site at the moment is it's quite exciting, in my opinion. We have, for example, the Owens Valley log wavelength array led by Greg Hallinan, which makes all-sky images between 30 and 80 megahertz every second or so. We of course have the 6 10.4 meter dishes, which once were part of the Owens Valley millimeter array, but are being refurbished in one case with a 19 pixel multi-beam receiver for high redshift CO intensity mapping. And we hope to use other elements of this array for EHT science, as well as a centimeter and millimeter wavelength photometer in the radio for time domain applications. We have an experiment led by graduate student Chris Bohenek to search for the nearest, brightest fast radio burst using anti-coincidence between different sites. We have a 40-meter dish that does various kinds of AGN monitoring and is famous for CMB experiments and VLBI in the past. And we have a solar interferometer and, of course, the deep synoptic array, the DSA, which is designed for FRB localization. So there are many, many telescopes that have, in this case, published papers searching or having detected fast radio bursts. There are many telescopes that are doing this job. They range from large dishes, of course, like Arecibo and Effelsberg down there, the GBT, to arrays like the VLA, ASCAP, the EVN, VLBA, Westerbork, basically any radio telescope that you've heard of, not millimeter, but radio in particular, has probably published a paper in FRBs. And almost everyone in the world, every radio telescope, is searching for them at the moment. You even have these little TV antenna-like things over there, which in this case actually claim to have detected some. I mean, it's still an early claim, but they actually claim to have detected some. And so, of course, we'd like to add to this. But the one thing I'll emphasize is that, unlike all these telescopes, the program that we're embarking on is the first one that's actually purpose-built for FRB detection and localization from the ground up. And so what is this? So over the last few years, I led the construction of a 10-element prototype, the DSA-10, which consisted of 10 4.5 meter antennas operating at L-band, 1.4 gigahertz. And we do interferometry with a 1.3 kilometer baseline, not very long. And our demonstrated localization accuracy on Crab giant pulses, so giant pulses from the Crab pulsar, is about 5 arc seconds. And yeah, it's a nice prototype. What this has led into is the full deep synoptic array, which has been funded by the NSF MSIP program. And this consists of 110 5-meter dishes, again operating at L-band, but now coherently searching for FRBs. And we've got slightly better localization accuracy with a larger baseline. What we hope that this will lead into is something a bit beyond FRBs, a 2,000 element array for various kinds of radio science. And I'll say a little bit about that at the end as well. But first, DSA 10. Building instruments is really fun. I encourage those of you who haven't done it to go out and try and at least get involved with a bit of instrumentation. It is a lot of fun. We bought these dishes off Alibaba.com, $1,700 each, including shipping, amazingly enough. They look like dishes. It's a start. Sandy Weinreb, for those of you, sorry? Yeah, never know. Sandy Weinreb, who will be familiar to many of you in the audience, is a key member of our group and has led a lot of the analog electronics development for the group. Sandy's pictured up there. We have a very crude range setup to test our custom-built feeds. In this case, we used off-the-shelf LNAs and tried to use sort of open-source software where possible to develop the digital side. Our configuration, 9 of our dishes sit on this T-shaped structure at Owens Valley, which used to host the millimeter array. One of them is out here to provide an extended baseline. That's our PSF. It's not terrible. It's good enough for our purposes. Here are 4 of the dishes in a sort of preliminary configuration where we wanted to test beamforming as well. They look kind of nice. The feeds are up there, little amplifiers near them, electronics in the boxes there. Yeah, they look great. They work. They work really well, in fact. This is a pulse, one of about 350 or so pulses we saw in about 50 days from the Crab pulsar. Looks nice. You can see the nice little dispersion sweep. There's the dispersed pulse, and it images pretty well as well. This is the image, and this is the PSF. And you can see the key thing here is that we detect in the incoherent sum of all antennas, but then having detected something, we can store data and then coherently combine, much like people do in VLBI experiments, to localize the burst. Our field of view is about 3.5 degrees across from full width half max. We make 7 by 7 degree images for each event. So this served its purpose. It demonstrated the technology. And so we proposed and were successfully and were awarded an MSIP grant to build the 110 element DSA. And so this modeling of the population that we've done suggests that we will localize over 100 events per year. Commissioning is expected to commence midway through next year, with full operations at the start of 2021 or so. And so the idea is that we have 95 antennas sitting on the T-shaped structure. We're basically filling it with as many antennas as we can possibly fit. And then 15 outriggers scattered over the site. This is sort of a picture of the whole Owens Valley site. And the main idea here is we wanted something that was almost guaranteed to detect as many FRBs as possible. And so what we built is something almost as sensitive as the Parkes, well, designed, is something almost as sensitive as the Parkes telescope itself, which initially set our knowledge about the population statistics. And so the idea is that regardless of, for example, the source counts, we expect to detect a lot of FRBs. That's the DSA, and we've passed our preliminary design review. Our final design review is expected to be in early July. Our first dish actually arrived last week, and so things are happening as we speak. Things are being built as we speak, in fact. And so finally, DSA 2000 is a concept to be submitted to the decadal. You might have noticed in the previous slide that the total cost, construction and operations of the DSA 110 was about 5.3 million, which suggests that you can scale that up quite well within a fairly small cost cap. And so our proposal is to build a 2000 dish array, not just for FRB science. In fact, FRB science will be almost commensal. But the idea is that we can conduct all-sky surveys with a fairly rapid cadence, down to a couple of microjansky RMS. The idea is that we also will support the nanograv pulsar timing array to actually time about 200 millisecond pulsars for gravitational wave detection. And we also expect to support LIGO follow-up in the radio. And finally, we expect to have coherent beams for both FRBs and VLBI applications. The main selling point is the survey speed, the time it takes to get to survey a patch of sky down to a certain depth, which, as designed, as spec'd, is about 10 times that of the first iteration of the SKA, with, of course, slightly worse angular resolution as well. This is really a radio survey instrument, not something for pointed observations. As some of you will be familiar, the NGVLA is very much a pointed telescope. This is pitched as a survey equivalent. We have some nice configuration studies, and several bits of work are underway at the moment to try and bring this into a coherent picture. And so, to conclude, FRBs are really, really fascinating things. It's a very, very exciting field to work on. I've got a lot of satisfaction out of it, and I think that it's a really exciting time to actually be working in this as well, because just of the sheer amount of data that we could expect in the coming year, I would say. And so, although the universe, I think, can probably make FRBs in many different ways, I do think that data are pushing us towards a somewhat coherent picture of what they are. I would argue that the sources of FRBs need to repeat. Therefore, they need to be somewhat long-lived. I would argue that they're likely to be compact objects, potentially highly magnetized as well. I think that's about all that we can say in a fairly robust way at the moment, given the data. I would also argue that we're only skimming the surface of the phenomenon, that there are probably a lot of FRBs that we are not sensitive to, that we would be if we built bigger telescopes. I also think that the progenitor problem is something that's probably not going to be all that easy to solve. Unlike the amazing progress made with the first gamma ray burst localizations, we don't really have afterglows here. And so there isn't a lot you can really say about the kind of, I guess, explosion that occurred when an FRB was emitted. It's going to take longer-term characterization of the host galaxies, the progenitor environments, and links between FRB properties and those things. It's going to take probably a few tens of events with careful studies of host galaxies before we can really zero in on a single progenitor scenario. But of course, I will emphasize that I think that a few objects that are really special, maybe they're really nearby, maybe they repeat amazingly frequently, they will, as always, probably drive the field as well. But I would also say that we're quite hopeful that the next decade will see large FRB samples also being used to probe unseen matter that we can't otherwise probe. Thank you.
Ramesh.
Excellent topic.
Thanks.
Actually, I have many questions. I have one.
Sure.
So, the scattering, which causes the profile to be broadened, right? And you kind of mentioned one picture where the scattering clouds or cloudlets are distributed more or less homogeneously between us and the source.
Yeah.
Another limit might be that it's just one halo or something which is doing most of the scattering.
Yeah.
Now, they do have different signatures. I think the single scatterer gives, like you said, the perfect one-sided exponential, but the homogeneous guy will have a different shape.
It's slightly different, yeah.
Can you tell from the data which one is actually operated?
Not yet, because we don't quite have high enough signal to noise. I'll be very hopeful about doing it with repeating events. For single events, it's a bit hard. The other issue is, of course, you don't know exactly, you don't really have the distance scale for the scattering medium, which complicates the picture a little bit. It makes it hard to distinguish between sort of a scattering medium that occupies maybe 10% line of sight or 50% line of sight, or is isolated into a small region. Maybe there are multiple screens as well in some cases. I think it's generally a complicated picture, but certainly with repeating events, I think we'll be able to do it. Yeah. Yeah.
Harold?
In the space of angular resolution and frequency, what is the smallest source that you've seen in an FRB, the smallest angular size?
So we haven't resolved them in a spatial way, but we've certainly resolved them in temporal.
In what?
And we've certainly resolved them in time. The smallest timescale we observed inside in an FRB is about 5 microseconds or so. Yeah.
So, do you have any plans to look at the smallest angular size?
I would say that not so much being in particular, but certainly the CHIME group is hoping to build VLBI stations. The biggest thing you'd learn there would be the scattering itself, because you can try to break some degeneracies in the scattering behavior. Exactly, yeah.
Igor?
Do you have any chance of detecting them with LOFAR? And if yes, has anyone tried to look for them in the archive?
People have certainly tried, and people are also trying in real time. I think that people weren't very excited about it until CHIME showed that they existed at 400 megahertz, which wasn't known previously. But then what it'll also say is that, and there's a paper in the archive that we published, I think it was yesterday, where we showed that the rate at 800 megahertz is quite a bit lower than what you'd expect from the higher frequency rate. And so the chime rates are, although large, it's unclear what they actually are as yet because they're not calibrated. So although low-fi may be able to see them, they might not see them very often. I think that's the problem.
I would like to salute your attempt to find a coherent, unifying model with ingredients that match everything we know, but there seemed to be a tension in this statement that you made. On the one hand, in order to avoid the abundance being similar to core collapse supernova, you need them to repeat a lot. But then there are only 1 or 2 out of 70 that repeat. So, I mean, in order for that to hold, you need at any given time to see a lot of repeaters. It's not enough that during their lifetime, because otherwise the numbers would not work out.
Agreed.
Given the fact that repeaters are so valuable scientifically, and people are searching for them, and they haven't found so many. How do you reconcile this tension?
I think there's 2 parts there. One is that we haven't followed up a lot of FRBs for a long time. And so I think I might have an extra slide somewhere or the other on this, but the thing is that some FRBs really do look a lot like, here we go. So some FRBs are simple, but some FRBs are not. And so the point is that repeaters, as we've seen so far, are not simple. And so it's unclear how many repeaters are hiding within the population we have already. That's the first thing I'd say. The other thing is, I think we haven't done enough work on understanding the range of timescales to which we're sensitive for repetition. I mean, the reason why the first one was found is because they just thought to look again, but so did a lot of other people. They also thought to look again, and it's unclear whether we're sensitive to sort of few month repetition timescales or a few year repetition timescales. We're generally sensitive to timescales within the span of observation. So I think my suspicion is that this tension can be reconciled by there being more repeaters within the population.
Great talk. I have a 2-part question. What do we know about the spectral index in the transient part? You showed for the first. Right. And the second question is, what do we know about the polarization? I mean, does the polarization speak to anything?
So let's see. I have a slide on polarization too. I'll come back. So first in the polarization. Anywhere between 0 and 100%, with no speed. Some are 0, some are 100. Some have a bit of circular, some are 100% linear. But the limits in the cases where we don't have polarization are not incredibly constraining. They're only down to 4 to 10%. The spectral index is difficult, but for a few reasons. One is that they're mostly discovered in pulsar surveys, which means that people don't calibrate their bandpass. And so it's when people have made the effort, for example with ASCAP, they find that the bursts typically have very patchy spectra with sort of a few islands of bright intensity, which may be scintillation or scattering. It may be intrinsic. It's hard to separate that out at the moment in those cases. When they sort of take the median of all their events, they get a negative spectrum of about 1.6, I think. But if you extrapolate that down to even 800 megahertz from L-band, it's inconsistent by about 5 sigma with the rate at lower frequencies. And so if the spectrum is negatively sloped at higher frequencies, it almost certainly has to turn over at lower frequencies. The spectrums it's all over the place. The repeater, for example, has those very strange the islands of emission, sort of parade down to low frequencies.
So the one with the high polarization doesn't do anything over the burst. Does it do anything on the station?
There have been some cases where it does appear to do something, but it's unclear whether that's a calibration artifact or not. In other cases, the bursts are barely resolved in time. The shapes you see are the instrumental timescale. millisecond response. And so in those cases, you also see it sometimes do something, sometimes not, which is definitely a calibration problem. But yeah, it's I would say there's no evidence for there to be a swing.
So, okay, Tony?
How steerable are those 5-meter dishes?
So the ones we have at the moment are not. We move them by hand. The ones we're building right now move in elevation automatically, but the ones we're proposing will move in azimuth and elevation. We're actually specifying 0.2 degree pointing accuracy, which seems actually a bit of overkill, but it's needed to image things out in the side lobes.
I'll take the last question. What does long-lived mean to you?
Over a few decades.
Well, not very long by astronomical standards.
No, that's right.
Okay. So let's thank our speaker as well.
Yeah, I know, including Faraday conversion, which I would like to actually, ask you a lot about.